Hi everyone, welcome to this session. We're happy to be here. So today we'll go back to the roots. We'll find the origin of content security policy bugs.
Yeah, so I'm Tom, this is Gert-Jan. We're both researchers at the University in Leuven in Belgium, where we do all sorts of research related to web security and privacy. And now Gert-Jan will give a brief introduction on the research that we did.
Thanks, Tom. So why exactly do we want to find the origin of CSP bugs? Well, as you can see from these article headlines, it's still a prevalent issue. These report on bugs against security policies. So it seems that browser developers still don't seem to be able to prevent all these bugs, right? So to find the origin, we hope to actually find the reason as to why they can be prevented that easily. So first, a bit of context. What is the Content Security Policy, or CSP for short? So it was introduced about 10 years ago as a defense in depth against content injection attacks, like, for example, cross-site scripting. And essentially, when you visit a website, that website has the opportunity to include a CSP, and then client-side in the browser, that policy will be enforced. So CSP is what they call a living standard. Throughout the years, a lot of new features, new use cases have been added. Nowadays, we're at level 3. Just to be on the same page, a small example. Let's say this is a social media website, and this in particular is a web page that presents the profile page of a hacker. And despite the content sanitization countermeasures of the social media website, the hacker was able to still inject a script. Now, if any visitor of this web page will have their cookie leaked. Now, the website can prevent this by putting up an extra layer of defense, being CSP, and this policy will effectively block the injected script. Now, as we saw before, the implementations of these policies can have errors, and this also makes it more easy for the developers to circumvent this policy, right? And in this case, maybe the hacker could circumvent this measure to still execute the script. Like I said before, CSP was introduced about 10 years ago, and throughout this time, a lot of bugs have been discovered, as we will see later on. So the central question of this talk is, what is actually the origin of these bugs? Because if we know the answer to this, we can use it as an attacker. We can find out where to find the next bug, but also as a defender, we could find out how to prevent the next bug. But maybe the most important question for now is, how are we gonna find these answers? And for this, we looked at the smallest recorded code changes that introduce or fix a CSP bug. So for this, we used code revisions. So these huge browser code bases, they use version control systems like Git, for example, to track every change that is applied to the code change. Here, every green dot stands for a snapshot of the code base or a Git commit or a code revision. If we combine that with proof of concepts of known bugs, we can then use dynamic analysis to find out what snapshots of the code base are vulnerable. In this case, the red squares. And this, as a result, gives us the code changes that actually introduced or fixed a bug and the associated metadata. Now, this is very nice, but these browser code bases, these are huge. They consist of more than 1 million code revisions, and still each day more than 100 are applied. So doing this manually is not very feasible. And for this reason, we developed Bughawk, which will automate the lifecycle analysis of these browser bugs. So essentially, you give Bughawk a proof of concept of the bug you want to analyze, and then it will find the introducing and fixing revisions. Now, this looks a lot like a bisection tool. That's because it is, but it also sets itself apart from all other bisection tools. This is because these binaries are executed in their own container, so we take care of all dependencies. This makes us able to evaluate even very old browsers. We can go back in time to Chromium and Firefox version 20. Also, we can run these evaluations concurrently to speed up the full evaluation process. This we used in a study to evaluate 75 CSP bugs, and we found some very interesting things here. First of all, we looked at the code changes that introduced these bugs. And more specifically, we looked at the intentions of the developers that applied the bugs. It turned out that half of the bugs in our dataset were already introduced at the very first revision that CSP support was introduced. These are called foundational bugs. A lot of these lived under the radar. Even one bug with a bounty of $5,000 lived under the radar for 8 years. Also, modifications to CSP logic are very prone to introduce new bugs. For example, even fixing a CSP bug is prone to introduce another CSP bug. Then also adding features that are not really related to CSP, but should be scrutinized, also caused bypasses because of oversights of developers. We also identified a lot of room for improvement for cross-browser bug sharing. So if a security bug is reported for a browser, it will be shared with the other browser vendors because they share the same functionality, same specs. The current practice uses the web platform tests. So essentially, it's a public Git repository, and regression tests of security bugs are pushed there, and other vendors can then pull these to check if they're affected as well. We evaluated this process by performing cross-browser evaluation between Chromium and Firefox. So essentially, all bugs reported for Chromium in our dataset, we tested for Firefox and vice versa. So we started with the 75 unique bugs. Of these, 14 could be reproduced in both browsers. These were shared. And 8 of those were only reported for one browser. Now, more interestingly, 7, so half of the 14, could have been reduced in lifetime or even completely avoided at all if communication was more effective. Now, we also extended the evaluation to the release of Safari. This was 16.2, and here we could reproduce 4 of the publicly disclosed bugs. Of course, we reported the issues, and this resulted in 3 fixed and 1 not considered a bug. Very important here is that Safari was exposed to these publicly disclosed bugs for more than 1 year. And this is something you really want to avoid as a browser vendor, but it even gets a little bit worse. We also identified inconsistent bug handling, which led to premature disclosure. So in 3 cases, the bug was publicly disclosed by the browser vendors themselves before they landed an effective fix. This was the case for 2 Chromium bugs and 1 Firefox bug, and in each of these cases, it exposed the browser for more than 1 year. Even in the case of the Firefox bug, this one was still present in the latest release at the time of our evaluation, but again, we reported this, and this was fixed.
Yeah, so as Gert-Jan mentioned, there were like 3 main issues that we found with related to the lifecycle of a bug. Namely, like when there's an introduction, it's more likely that there's other bugs there as well. Like there might be also bugs that live across different browsers and the way that they're handled. So in the next few slides, we'll explore how we could use this either as an attacker. So I'll play the role as attacker, which could be like a bounty hunter, a red teamer, or a security researcher looking for bugs in the browser. And then we'll also look at how we can defend against these. And Gert-Jan will be playing the role of the defender. So whenever there's a change made to the core logic of CSP, it's quite likely that more than a single bug will be introduced. That's because, well, we did this analysis of these 75 bugs, and that's kind of what we found. So as another thing is when there's things like iframes or other sorts of inheritance of the content security policy, the enforcement of that is pretty difficult. Now, the third thing that we found is when we have the script source directive, which is pretty complicated compared to the other directives, those are also quite likely to introduce all sorts of different bugs. And also the way that the content security policy is enforced in the browser because it's been, because first we had all these different features, and then afterwards we retroactively applied content security policy to that. The enforcement is quite fragmented, which means that sometimes browser vendors might miss something, and there might be a very simple bypass. So how can we use this as an attacker? So we can look at the different public bug reports, because security reports become public after time they've been fixed. And we then might use a tool like BugHawk to find which revision introduced the bug and which one fixed it. So we can look more deeply into the introducing bug, because as we found, it's quite likely that there will be other bugs introduced in the same revision as well. And we can also look at the fix and see whether the fix is complete, covers everything. And we can even compare it with the introduction to see if everything was fixed correctly. Then we can also use some sort of heuristics, because we know, like, when there's code touching the core CSP logic, or there's some sort of inheritance logic, it's more likely that there will be a bug. So we could use all sorts of different heuristics. And then as an attacker, we can more easily focus on the different pieces of the code that are more likely to be vulnerable, or we can figure out whether a bug is, or a code change will be more likely to introduce a new bug. And ideally, we would also automate this. This is something we're not quite yet at with BugHawk, but maybe in the near future, we'll get there.
Okay, how can you use this as a defender? Well, based on our data, we found that centralization of enforcement logic really helps. It really reduces oversights that introduce bypasses. An example of this is the inheritance-related bugs. We found in total 22 inheritance-related bugs, and 20 of those affected Chromium, and only 2 affected Firefox. Now, this is the case because Firefox did a much bigger effort centralizing this enforcement. Now, later on, Chromium developers also did a huge effort by putting CSP enforcement in the policy container. And this was landed in 2021, and this immediately resolved 7 of these inheritance bugs. So as is kind of similar with the attacker, the defender can also assign more resources based on heuristics or likely culprits. In this case, for example, it should really pay more attention to changes to the source code that are likely to introduce bugs. And this means, for example, assigning more reviewers, creating more tests. And going further on these tests, in the ideal case, these would be automated. And actually, we found that a lot of these bugs that were part of our data set could have been prevented by very simple generated tests. For example, if you add a new feature, you can test it against the most strict possible policy. And in the case of CSP, for example, when a request is still sent, this indicates a bypass. And you can also take this strategy when a new policy is introduced, for example. So as we've seen, we also identified a lot of room for improvement, considering sharing of bugs among vendors. Quick recap, so 7 of the 14 bugs in our dataset that were shared could have been prevented or reduced in lifetime. And 4 public bugs still affected the release version of Safari. Also a little detail, so 5 of the 14 foundational bugs in Chromium later appeared in Firefox as a regression bug. So this means that it really makes sense to still include regression tests of other browsers, even if you're not affected from the start. And you would think that these regression bugs might have been features that Chromium added way ahead of Firefox, but this was not the case. These regression bugs were introduced due to CSP bug fixes, and this was in 4 cases. due to a bug fix, but in one case it was also due to a CSP enforcement design revision.
So yeah, what can we then do with this as an attacker? So we know that like these bugs get publicly disclosed, and some of them might already contain certain tests. So a very simple thing to do is just run the same test in all the different browsers. And as was the case with, well, at least Safari and Firefox as well, we might already discover some new bugs. Unfortunately, not all of the fixes and the bug reports contain web platform tests. So if there isn't one already, then it's sometimes fairly straightforward to just write one and then just keep on testing until you find that the new browser version becomes vulnerable to it. And then, yeah, next to looking at the browser bug reports, we can also just look at the web platform tests and use kind of that as a sort of inspiration to find new types of bugs. So we can take a test for one particular bug and make some small adjustments and then see if this would be applicable to other browsers possibly as well to find also new bugs.
As a defender, bug sharing platforms you use should be obviously representative, and this means consistent sharing of bugs with other browser vendors. In the short term, this means maybe changing the sharing practice. We identified a lot of disadvantages with the current practice of using the web platform tests repository. For example, sharing is postponed. It's only done after creation of a regression test. Sharing is public, so when it's pushed to the repository, it's public to the world, and then the other vendors have time to react, essentially. And there's also no security focus. We think it would be better to use a privately shared bug reporting platform. This enables sharing bugs as soon as possible, even right after triage. Also, sharing is private, and vendors can even disclose the bug in agreement. And there would be ideally a distinction for security bugs. And in the long term, we also think that browser vendors can learn from each other as to how they actually solve the same bug.
Yeah, and then the last thing that we wanted to highlight was the handling of bugs, and for instance, the way that they're being tested and being mitigated. So we found these three bugs that were prematurely disclosed. So for instance, two of them were regression tests, because in one case, the tests contained a meta tag instead of a header, and that caused the test to succeed while the vulnerability was still there. And then another bug was in Firefox, where the bug would exist in the package build, but not in the non-package build, and the non-packaged build was the one used to run the test. And then a last case was when there was a fix in Chromium, that's where the fix was eventually reverted, but this was not reflected in the bug reports, so the developers thought that the bug was fixed while it was actually reverted, and the vulnerability was still there. So what we can do then as an attacker is that, again, to see if there's any regression tests or fixes, and to check whether these are complete and sufficiently covering all the different issues. And even we can look at differences in the test builds versus the actual release builds, because the release builds is the thing that we actually care about, because that's the things that actually run on the user's devices. And whenever there's a revert, that could also be like looked at as a sort of red flag to kind of raise the awareness of the attacker and tried to look into why it was reverted and was it correctly applied, and was it later on, was there actually the fix re-landed? And if that's not the case, then that's a very easy bug report to make. And then finally, the attacker could also monitor certain lines of code of a fix. Because if there's adjustments being made to the fix, then it might be that the fix becomes undone, and then the vulnerability will be reintroduced as a regression. So that could also be valuable for an attacker to look into that specifically.
As a defender, it's really important that regression tests are an inherent part of the fixing process. First of all, as a sanity check, did the fix really work in the intended way? But also in the long term, we could use regression tests to find out what code change actually introduced the bug. In our data set, the bug reports in 87% of the cases actually identified the fixing revision. You would think that this is 100%, but in a lot of cases, developers didn't really know how the bug was fixed. These were primarily bugs that took a long time to actually fix. Then the identified introductions. Here, bug reports only in 6% of the cases really identified these. So consistent and comprehensive testing is very important. As Tom already mentioned, it's really important that binaries should represent the release binaries as much as possible. And also, the tests should be independent of policy delivery, whether it's delivered through meta tag or through the header. And then also mentioned for the attacker is the red flags, so diversions from the default fixing protocol should be indicated as a red flag. And here I'm talking about reverts and relents, for example. Okay, we've arrived at the last slide. Just some key takeaways of this talk. First of all, we think that bug life cycles are a much needed tool to better understand bugs. This is both from an attacker's and a defender's perspective. We also found 5 issues by just looking at publicly disclosed bugs, and these issues affected releases. So browsers, they implement the same specs, and as such can be vulnerable to the same attacks. Some bugs were only reported for a single browser, so it makes sense to really effectively share these. And we think that for this, a back channel is needed instead of the web platform tests that are currently being used. We also found several instances of bug mishandling. Some were publicly disclosed before the fix was effectively landed, and this was caused by incomplete regression tests and also by an unreported revert. And as a last point, I want to mention that BugHog is open source. It's free to use. You can use the QR code to visit our GitHub page. And with that, I will conclude the talk. Thank you.
Take questions? Thanks for your talk. So as you went through the identifications of the moments where bugs was introduced, did you also check the author of the changes? Has any pattern come out of that? Should we start blaming the people who actually introduce if they do that repeatedly in particular?
We didn't actively compare the authors, but I think you will always see the same names because the teams that work on CSP, for example, these are quite small, I'd say. But we didn't look at it, but that might be an interesting statistic as well.
If there is no other question, so you have done that for CSP. How reusable is your framework to look at, I don't know, XZ archive, for instance, or something like that, XZ utils, these kinds of things?
Essentially, if you can make a proof of concept in a website that just requires, that just sends a request to a certain endpoint when the bug is reproduced, then it can be integrated as such in our framework. So I guess it's, we already tried it for evaluating HSTS, for example, also cookie policies. So it's, I think it can be widely used for other policies as well.
And yeah, maybe in the future also things unrelated to the browser might be applicable, because we already have like the whole infrastructure to run things, run the different tests. So as long as we have like a repository with the different commits, we can already start identifying what caused the issue and what fixed it.
Questions? Thank you again.
Yeah.